Exponential form of a complex number. From polar to exponential. We've already written complex numbers in polar form as z is equal to r cos theta plus I sine theta, or using the contraction r cis theta, where r is equal to mod z is the modulus of our complex number, and theta equals arg z is the argument, which, as we've said before, is usually in radians between negative pi and pi, with the negative pi not included and pi included. Euler discovered the remarkable identity e to the I pi is equal to cos theta plus I sine theta, and therefore is equal to cis theta. This is not that difficult to show. One way of showing it is using Maclaurin series, which we'll do later in the course. This means that every complex number can also be written in exponential form. Z is equal to re to the I theta. So r gives the length of the vector, its modulus, as before. E to the I theta describes its direction, rotating anticlockwise by theta radians from the real axis, the positive real axis. This is simply a more compact version of the polar form, but it's vastly more powerful when multiplying, dividing, or raising complex numbers to powers. So, comparing the three forms, Cartesian form, z is equal to a plus bi, that's useful for addition and subtraction. It's much better for addition and subtraction than polar or exponential. Polar, z is equal to r cos theta plus I sine theta, or just r cis theta, highlights magnitude and direction. Exponential, z is equal to re to the I theta, is best for powers, roots, and rotations. Though I have to say, and you may notice this, I tend to revert to cis form quite often when doing things, just because I'm more familiar with it. Connection to Euler's beautiful equation. Euler's identity, e to the I pi plus 1 equals 0, or sometimes expressed as e to the I pi is equal to negative 1, links the five great constants, e, I, pi, 1, and 0. Should note that pi is the most used constant in all of mathematics. E is the second most used. Both of these are irrational numbers. They have infinite decimal expansions with no recurrence. I is an imaginary number, as we know. But when you combine it in this form, you just get negative 1. That is remarkable. It's the special case of e to the I theta is equal to cos theta plus I sine theta when theta is pi, since cos pi is negative 1 and sine pi is 0. Multiplication and division. So if we let z1 be r1 e to the I theta 1 and z2 be r2 e to the I theta 2, then z1 z2 is r1 r2 e to the I theta 1 plus theta 2. Multiply moduli, add arguments, as we're used to. And z1 over z2 is r1 over r2 e to the I theta 1 take theta 2, divide moduli, subtract arguments.